Welcome. My name is George Kraw. My wife, Rachel, and I have been sponsoring these series of lectures for the last 3 years to showcase the wonderful and important work that's being done by Santa Cruz technologists and scientists. Tonight we're going to learn about the use of games and adaptive technology to help people who are physically challenged, people with disabilities, and it's a very important area, something that will help many individuals and potentially allow them to be more active and lead more fulfilled lives. So our first speaker tonight will be Jared Duval, who's a graduate student at UC Santa Cruz, and he'll be talking about the use of serious games to help people read, to help people speak. And then we're going to hear from Professor Roberto, a very distinguished scholar who works in the area of helping the visually impaired. So let's welcome Jared.
Thank you. And I am working in the Assist lab and the Social Emotional Technology lab with Sri Kurniwan and Catherine Isbister. And I'm very excited to show you my work. We're going to be focusing today on my speech therapy game called Spoke It. And before I get into the game itself, I kind of want to lay the land with you for a little while. And I'm going to do that through some definitions, but they're going to be fun, I promise. So we're going to start down here with wicked problems. I'll talk a little bit about what that is and how we can work through some wicked problems with this methodology called research through design. And we're going to use that to create our serious games for health. But how do you make serious games for health? Well, we're going to talk about that with participatory design, and at the end, I'll show you Spoke It. So what is a wicked problem? Well, I'm from the East Coast, so we love to say wicked. But that's not what we're talking about today. A wicked problem is a big societal problem, like poverty or education or nutrition. And wicked problems are wicked because they're interconnected by nature, right? Education is linked with poverty, which is linked with nutrition, and vice versa, right? So how do you solve a wicked problem? Well, I can't really tell you. But I can tell you that the only way to poke at wicked problems is to learn about them, right? And one of the ways we can learn about a wicked problem is through design, and more specifically, research through design. So what is research through design? Well, research through design is different from what you might think of as research, right? You're studying a hypothesis, you're doing these, tests in a lab in the scientific inquiry. But, research through design takes a little bit different of an approach to acquire this knowledge, right? Through the act of making something and seeing what it does in the real world, you can learn about the real world. You can see what impact did this make, and then you apply your hypothesis, test the thing, see what happens. So we can start understanding wicked problems and maybe figure out how to make a better solution. Maybe not the answer, but something that was better than before. So I apply this research through design methodology in a thing called serious games for health. And before I can tell you what a serious game for health is, maybe we should, bring it back and talk about what a game is. A game is a structured form of play, distinct from work, played according to rules and decided by skill, strength, or luck, usually undertaken for enjoyment. Sounds about right, we all play games. So what is a serious game? Well, I hope some of you had a chance to play some serious games we have over here, but if you didn't, let me give you more of a formal definition, which is a serious game is a structured form of play distinct from work, played according to rules decided by skill, strength, or luck, but it's designed and targeted at a specific population for a primary purpose other than pure entertainment, right? So this can be defense, education, scientific exploration, emergency management, city planning, politics. Okay, great. So what is a serious game for health? A serious game for health is a structured form of play distinct from work, played according to rules and decided by skill. It is designed and targeted at a specific population for a primary purpose to help that population achieve their goals in a medical or well-being context through enjoyable mechanics that teach a skill. And I really want to highlight this part right here. Enjoyable mechanics that teach a skill, right? So we want to make a game, and we want you to play the game, and we want you to learn how to be better at something, right? A therapy, feeling healthier, feeling happier. And when you play the game, you should have fun doing it, because if you don't have fun, then you're going to put down the game, you're never going to play it again, and then your therapy didn't work, right? You didn't change the world, you didn't poke at that wicked problem. The other side of that is if your game is fun, but it doesn't actually do the thing it was set out to do, you're not really learning any skills, you're not making an impact, and again, you're not poking at that wicked problem. So the game has to do both. It has to teach a real-world skill, and it has to keep you motivated to keep playing. That's a difficult challenge. And when I say fun and enjoyable, I don't mean for you and you and you. I mean for the people that it's dedicated to, the specific population that that game is meant for. Right? So children with speech impairments are going to have a very different idea of what fun is than any of you in the audience possibly. So how do you design for these specific contexts and populations? I'm not going to pretend to know that I'm a child that knows what it's like to have a speech impairment, but I do know how to find them. So they're the designers. So we do something called participatory design, right? We go to these places, we talk to the doctors that work with these children every day. We talk to their parents. We work with the children themselves. And we figure out, what kind of game do you want to play? And how do we make it fun for you? And how will you pick it up again tomorrow to keep playing? So I'm going to go back to our definition. I've laid the land for you now. We got through the definitions. All right, so I'm going to propose to you my wicked problem, which is speech impairments in children, right? Healthcare system in America, it's really expensive. It's hard to get access sometimes to specialized professionals. So we're going to talk about this wicked problem a little bit. And I'm going to give you some numbers. 1 in 12 US children aged 3 to 17 have a voice, speech, language, or swallowing disorder. 34% of those children have multiple conditions, and 25.4% of those children have multiple communication disorders. 55.2% of those children who needed intervention services receive them. It makes you think about, what about the other half, right? Up to 70% of speech-language pathologists in America have a waiting list indicating a shortage in the workforce. So people who need speech therapy can't get it. Boys are more likely than girls to receive intervention services, and white children are more likely than Black or Hispanic children. So this is a big problem. And, a game is something that's, especially if it's free and on the App Store, something that's easy to get and can make a difference, and it should integrate into the healthcare system that already exists, right? You bring the game into your speech-language pathologist's office, the speech-language pathologist can say, oh, you made progress, great, we can start here instead of refiguring out where you were, where you left off. And I want to talk about the implications of these wicked problems, right? Children with speech impairments are higher at risk for depression, deficits in social skills, delay in scholarship, lower income. So we need a way for these children to improve their speech, because I'm going to argue that speech is a skill. And just like any other skill, it can be worked on, it can be improved, you can practice. And typically, it's a once a month, who knows, you get to see the speech-language pathologist. You go in and you reevaluate it, and you're given a whole bunch of homework, you take it home, and the parents are supposed to just facilitate this, right? And how many of you are parents in the audience? Would you feel ready to conduct a speech therapy session with your child, not being a speech-language pathologist? This facilitation is hard. So if we can create an app that supports this going on at home, then we can make a difference at this wicked problem. So, how do we design this integration of speech? Research through design, back at that. So the first thing we did was we talked to medical professionals and people who work with these populations all the time, and we're like, okay, tell us where do we even start? And they gave us 3 requirements. Oops. 1, it needs to be offline. Many of our players are from lower socioeconomic statuses. That's why they can't see the speech-language pathologists. They don't have access to the internet, so they need a speech recognition that's offline. And that kind of rules out all of those things like Cortana and Siri and, all those different speech services. And also, those would create lags, right? Because the internet is slower than a thing that happens directly on your device. It needs to be mobile. Mobile technology is pervasive, it's accessible, it's affordable, way more affordable than health bills. And it needs to be critical. So if the speech recognition technology isn't telling you how to do it better, then it's not really working, right? You need support. How do you say this word even better? I heard that you said it a little bit wrong. And here's how to do it better. So those are our 3 requirements. And we got those from all these professionals, and we jumped right in. And we found this technology called Pocket Sphinx and Rapid Ears from Carnegie Mellon University. And I'm going to just show you a real quick example of how it works, right? So this is what the computer sees. It's just, waveforms, right? It's sound. This is their speech. And they're saying, move the rock, which would be the correct sentence, or moo the ra, which would be the incorrect one. So how do we represent that in computer world? Well, there's this thing called alphabet, which, if you can represent any sound through these different symbols. So all the different English sounds we can make are represented in this alphabet thing. And we just do some machine learning, and we can attach those representations into what they said. And based on what they said, we can know whether they said it right or wrong. And we can just teach it all the wrong ways they can say it. Okay, so now that we have the functional, the technology, we can do the thing somewhat well, how do you design the game? How do you make it fun? Well, we took inspiration from something that commonly elicits speech from children. So think Dora the Explorer. So we started with this storybook style thing, right? This is Sam the Slug, go Slugs, UCSC. And it's very linear, right? So you would say, put on boots, it would light up green as you say the thing, and then the next scene would happen. It's super engaging, super fun. Problem was, it didn't have you say a lot, right? You weren't talking all the time, and to create new narrative content was hard. It took a long time to do this art, and we can't keep doing that for forever. So it's not as therapeutic as we wanted. So we're like, okay, let's rethink what we're doing. What kind of fast-paced gameplay can we use? So we were like, okay, let's do a arcade game, right? So you just touch the thing, it tells you different words to say, and as soon as you say it, it blasts off, and you can do all different kinds of words, and it happens fast. People didn't want to play it a second time. It wasn't replayable, right? So we're like, okay, well, people love the first one for replayability. This one's more therapeutic. What do? We do both at the same time. We make a hybrid structure where there's narrative content surrounding these mini games. Let's try that. But this is kind of where I took over the project, and I said, listen, we need to look at how we can really make sure this is going to work, because I don't want to keep investing time in something we don't know is going to work. And that's when I found out about participatory design, which we talked about earlier. Please, Mo. So participatory design with Serious Games for Health. We, again, went back to stakeholders, and this included children, adults with developmental disabilities, doctors. We went downtown in Santa Cruz to Hope Services, to adults with developmental disabilities, co-occurring with speech. So we engaged with all of these populations. We're like, what game do you want to play? I don't want to be a designer today. I want you to be the designers. So how do we do that? Well, I'm going to say how you interface with the population is super important. It's all about context, right? So I talked about this overarching plot. We have these characters, the MIGs, and they're this speechless race of characters. They can't talk. And we have this narrator, Nova, who can talk, but her magic is powered by speech. But because the MIGs can't talk, she can't be charged by the MIGs. So the player has to use their voice to charge Nova and get the MIGs to live happy, healthy lives. So we have our design probes, right? Children love to play with toys, so we're using that, we're leveraging that. What are these other toys for? Well, they're not just random. This is developmentally appropriate words that the speech language pathologist might have them play. Or it's a random number generator or a random letter generator. Say a word that starts with C 3 times, right? So you're getting those mechanics out of the tangible tools. And of course, draw your experience, write it, and then we'll rapidly iterate it in the digital world. So this is some kind of new fun things that we've been working on at UCSC, is being able to rapidly prototype with users in real time on a thing that they can then experience on the iPad, right? So they're creating the games with us, and within the end of the session, they're playing it on an iPad, which is super fun for them. And it also makes it so they can give us immediate feedback, so we're not spending a whole bunch of time designing, going back and realizing we did it all wrong. We can figure out the design right away. We went back to doctors, and they had even more feedback for us. They were like, okay, well, your characters, they can't speak. How do they communicate? Through emotions, through facial expressions. Nova, she should be exemplifying how to say speech correctly, not just hearing how to say speech, but show you how. So we came up with this technology that can let you rapidly make these lip sync animations and show the children how to speak. So enough of me talking. I'm going to talk more because it's a speech therapy game. But I'm going to attempt to do a live demo of Spoke It for you up here. So if you'll just give me a moment to swap over. We'll see if we can get this up and running.
Been listening to and recording.
We're just going to restart it.
Well, hello. It's great to meet you. I'm Nova, and I've been listening to and recording the stories of the Spoke It universe for many, many years. But today, I'm about to star in my very first story. I'm relieved to meet you because my light and magic are powered by speech, and I could use your help filling me with speech magic. That's right, your voice gives me magic. Let me show you. Just say a color.
Purple.
Neat, I'm purple. That was fun. Keep in mind that I can only be powered by speech when I'm actively listening for your speech magic. But you'll know when I'm listening to you because you'll see stars dance around like this. Let's give it a try. When you see the stars, say a color.
Yellow.
Look, I'm yellow. Great. Let's do that 3 times in a row with 3 of your favorite colors. Oops, sorry, I wasn't listening. Make sure you wait for the stars to dance around the screen.
Blue. Blue.
Neat, I'm blue.
Pink.
I need to unclog my ears. What did you say?
Pink.
I need to unclog my ears. What did you say?
White. White.
Look, I'm white.
Green.
Look, I'm
And gray.
gray. There's no fooling you. You know that tapping the screen does not provide any magic, but your speech does. My magic comes from listening to stories, so I need to hear specific words that go along with the story. And you'll always know what to say next because I'll always show you pictures. Let's give it a try with these words. Start by saying comb,
Comb.
fun. Now the next one. Ooh, that's a tough one to draw. You can always tap on pictures if you need help knowing what to say. Go ahead and try it now. Try saying stack. I feel sparkles in my tummy. Now the next one.
Skate.
Great, just one more.
Coat.
You did great today. Your voice has given me the magic to explore. Let's get going and see where our story takes us.
All right. So again, I'm going to swap back over, which will take a moment, I'm sure. And where am I at for time? Okay. So, there's the tutorial of Spoke It. We have many other mini games that focus on regular articulation, rhythm, articulation, and fluency, and initial sound production. So words that start with a specific S sound or something similar. And, demos are over there if you'd like to see these mini games. But for brevity, we'll be releasing Spoke It, and you can check it out later. But thank you, that's my talk. Spoke It will be released soon. I hope you all had a chance to play all the serious games that are happening here at UCSC. They're really cool. And without further ado, I'd like to welcome Roberto Manduchi up to the stage.
is the title of my talk, Visual Without Sight, Finding, Reading, and Magnifying Text. I and my students work on access technology for people who cannot see or cannot see well. My lab is actually called the Computer Vision Lab. And that's because most of the technology we do is computer vision and AI. But in fact, we use a lot of other types of sensors and technology. So let me just start a little bit with some stats about the population that we try to serve. So on the top right here, we have a chart that represents all the US population. The cheddar cheese slice there is people with significant vision loss. These are people who have trouble doing things even with eyeglasses, maybe reading the papers, recognizing people from a distance. The very narrow green slice is people who are legally blind. In the US, legal blindness is an acuity of 20/200 or less in your best corrected eye, so very low acuity. Or tunnel vision, 20 degrees of field of view or less. That is a condition that occurs often with retinitis pigmentosa, for example, or with glaucoma. The really thin red slice is for people who are blind. And normally, very few people are really blind. Most blind people do have some light perception, but they have zero functional vision. So it is a very, very small community. But of course, people who are blind do have a number of special needs, if you want to. The experience of blindness is all-encompassing in all of the activities of daily life. I also have a chart that shows the distribution in age, that shows that among the people with significant vision loss, about 1/3 are 65 years and older. Not surprising. Oftentimes, vision loss comes from things like age-related macular degeneration or diabetic retinopathy that usually comes late in life. The reason why I point it out is because when we are at that age, oftentimes we have also other sorts of impairments. We may not hear well, presbycusis, we might have some arthritis, some mobility issues. And also, at that age, we tend to be a little bit less accepting of the super flashy new technology, new apps. And there's something you must keep in mind when you design this technology. So if you are, like me, an engineer, and you want to serve this population, what you should do is to make friends with people in this population and try to figure out what it is that becomes difficult to do without sight or with little sight. So I have a little list here of things that are difficult to do if you cannot see well, and I'm just going to read a few. You might not be able to drive your car, you might not be able to read a paper, you might trip over an obstacle, you might miss a sign far away, and a lot of other things. So as an engineer, you might want to pick and choose what it is that you want to address with your technology. Now, with my lab, we have addressed a number of these things. Many years ago, I started working on mobility devices. We wanted to replace the white cane with a very cool laser cane, which was a triangulation device using a laser pointer that would discover the distance to objects and would tell you if there is a step in front of you or something like that. Very bad idea. If you talk with anybody who is a proficient user of a white cane, it's actually called a long cane, they will tell you, don't bother. The cane works beautifully. It is cheap, it's robust, doesn't have batteries to replace, and it always works. So that was a big lesson for me. That's the problem with engineers. We tend to start with the technology. We tend to provide solutions, and then we look for problems. And it's very common, not just in this area. So it was very sobering for me. After that, I do spend a lot of time trying to figure out what are the right problems to address. One of them, for sure, is public transit. Now, if you can't drive your car, if you don't have anybody to drive you, if you don't want to spend everyday money for the taxi cab, or until the driverless Uber come and pick you up, you're going to use public transit. And I happen to be a strong believer of public transit coming from Europe. Just wish that in the Bay Area we had some better service. Now, if you cannot see or cannot see well, taking the transit can be difficult because there is a lot of information management when you take the bus or when you take the train. You need to figure out where the bus stop is, where you need to stand. which side of the street, is this bus coming, is it the bus that I need to take, where do I enter, how do I get off? A lot of information. So we have a fairly large project, also including the VTA, the Valley Transportation Agency, that tries to make public transportation easier to use for people who are blind or also people with cognitive impairments. Another thing that might be difficult with blindness is to find your way around. Imagine entering this building, this big building, trying to find a particular classroom, right? So we have a couple of projects that use smartphones for wayfinding. One project uses inertial sensors of the smartphone that track you as you walk around the corridor and try to give you direction where to go and how to walk back safely. We also have another project that uses a camera in a smartphone to use techniques like SLAM or structure for motion that help track the path of the user and again give some guidance direction. We have been interested in enabling access to documents. Now, back in the late 70s, Ray Kurzweil marketed for the first time what was an optical character recognition, OCR. I'm going to use this word a lot of times, which is a system that translates pictures of a document into text. So you would take the document that you want to have read, put it on a flatbed scanner that would be sent to a machine the size of a dishwasher, and that eventually would read the text for you, which is really great. Nowadays, the same thing is done in an app on your phone, and much better than that. So we've been working on human-computer interface that enable blind people to use this technology. And the things we worked on that I'm going to talk about today are screen magnification and scene text access. And I will start with the latter. So scene text is a technical term to mean any text that is posted on the walls anywhere in a public building. So if you walk here in the corridor, you notice posters, name tags. In a train station, there are plenty of this information. It could be directional information, directories, advertisement, and the like. This is information that is posted for sighted person to use, and we use that a lot. It would be great if even blind persons could use the same type of information. Now, like I mentioned, there is the technology out there, this OCR, optical character recognition technology, that can read for you. So it even works on a smartphone. It sounds like we are there. But we're not quite there. There is a usability problem that I like to call the computer vision without sight problem. And the issue is very simple. If you use a camera embedded in a smartphone to read things, this will work, but you need to first point the camera at the thing you want to read. But if you're blind, you don't know where the thing is. So I tried to show that in this graph here where you see a blind person aiming the phone, trying to look for something, maybe the emergency exit side, but she might not even know that there is a sign over there until she aims the phone to that. So that's what I call by the computer vision, the technology, but without sight, it may be difficult to use. So we started working on this problem together with my longtime colleague, James Kaplan from the Smith-Catwell Eye Research Institute in San Francisco. We did it even before the iPhone was out, before there was so much processing power and AI algorithms that could do a real good OCR. And so in order to study this and to study the human factor that goes into that, we had to invent a proxy. And these proxies are these color markers that you see here, kind of like a pie chart, that have been designed in such a way that software on these primitive cell phones, this is a Nokia N95, it was the coolest thing at the time, they would be able to very quickly detect that in real time. So there was no real text, but we pretended it was text, because the thing we really cared about is how can a blind person use a camera to find these things. Let me show you an example of that could happen. So this is an experiment in which a blind person is tasked with trying to find one of these markers and then walk towards the marker and touch it with their hand. These were one of the first experiments with blind people using smartphone cameras. You will hear some beeps during the video that I'm going to show. This is because the system, when it sees the marker within a certain distance, will start beeping. We'll also notice that there are more than one of these color pie markers. They're actually all different from each other. The system was programmed to only beep when it sees a particular one that happens to be on the left side of the elevator. So the The first thing you need to do is to try to find it. So you need to explore the scene with the camera. And is the sound connected? It is? Okay. So there was a beep. So this phone started beeping, and now she needs to walk towards the marker. How can she do that? Well, she basically follows her arm, right? Because the system beeped when the phone was aiming in that direction. This is a phase that we call guidance. Now, at some point, she mistakenly started aiming the phone somewhere else. The phone is not beeping anymore. So she needs to find the marker again. So she needs to, again, explore the scene to find that. This is the reacquisition phase. Eventually, she found it again, and she was able to walk towards it. She was one of the most proficient persons to do that. Some people, once they lose the marker once, it's very difficult to find. And that's because if you're blind and you don't have auditory references, anything that is beyond arm reach could be 1 mile away. You don't know where it is. So we did a lot of experiments of this type. We studied the effect of the field of view of the camera, the processing rate, and a lot of things. We learned quite a bit. In the meantime, this is, again, a summary of the search and guidance that is necessary for this. In the meantime, technology progressed, and eventually OCR was running in real time on your iPhone. So there was a time to try real syntax detection for blind people. The app that is really number one to do that is an app that was designed by Microsoft called Seeing AI app. It's kind of like a Swiss pocket knife with multiple functions. One of the functions is called short text. And it does just one simple thing. As soon as it detects, it sees some text from the image from the camera, it will read it for you. Let me show you short text in action.
Item 1 ACV, ACM career, 7up in membership, career membership, arena membership, MT membership SXRDS, ACM student magazine by student.
So first of all, I wanted to notice this system works really well. It's really fast. But if you paid attention, you might have had a little hard time to understand what it is they were saying. And it was not the problem with the system. The system was reading everything correctly. The problem was that he was not aiming it correctly to the scene. Again, a computer vision without sight problem. And if you only look at just one part of the poster and read at that part, everything looks a little bit funny. And he had no idea that he was not aiming at a full, complete poster. A second big problem of Seeing AI and all these applications is that they do not work when you are moving the camera. So let me show you here a little video in which I'm moving the camera with the Seeing AI app. And while the phone is moving, it seems not to be reading anything. And as soon as I stop the phone,
Controls, kitchen, clock, timer, on.
it reads everything and reads it very well. What's the problem here? Well, it's very simple. When you're moving the phone, like the frame shows there, your image is blurred. That's called motion blur. That's normal. And we can't expect the system to really work there. I don't think that even humans can read that correctly. So it's normal the OCR systems require steady state pictures. The problem is that if you don't know where the text is and you have to search it around, you need to move the camera. So to deal with that, we started working on what is called text spotters. That's another technical term that indicates algorithms that are able to detect the presence of patterns that look like text in the image. I don't read Chinese, but if I see a piece of Chinese text, I can tell, oh, that's text, right? So by doing so, they can be real fast, and critically, they can detect the presence of text without reading it, even when the text is blurred, which is exactly what we're trying to do. So we worked on that with my student, Jin Xiang, who now works for Google. And we developed our own text spotter. If you are into these things, that is a particular type of neural network. It's called a fully convolutional network that does a semantic segmentation type of thing. If you didn't understand anything for the past 5 seconds, that's perfectly fine. Let me show you some results of this type of thing. So you will see two images. On the left is an original image taken by a blind person while moving. To the right is the text that's been detected. So you see here just that it detects text on posters and everywhere. The system is really great, actually. It doesn't get fooled even by things that may look like text, but they are not. The text, even a small portion of text, and critically, it can detect text even when it is blurred. Great, that's what it wanted to do. Fine, but how exactly are we going to use that? Remember that the short text scene AI system does something very minimalistic. Looks at an image. If there is some text, it reads it for you. In our case, we have something a little bit more complex, and it works in this way. You input an image, and the system, if it finds some text, will vibrate the phone for you. Upon receiving this prompt of vibration, the user is supposed to stop the phone and steady it so that a high-resolution image can be taken with a steady phone, and the image can then be read through OCR. So in a sense, it's a two-step process, right? First, if there is some text in the area, you feel the vibration, you stop it, and then hopefully the text is read for you. Okay, so we had a system we called the Spot plus OCR, and we ran some user studies with 7 blind persons in our building, some extensive user studies. Let me show you one example of our system in action. You'll see a blind person here walking through the corridor. He was tasked with finding all of the text that was posted on the walls. You'll hear the system speak. Unfortunately, you won't be able to know when the system vibrates, but you know that when it steadies the camera, it means that it vibrated. Also, you will hear some type of indication such as rotate the phone. Unfortunately, OCR works well when the phone is really well horizontal or vertical, so we had to provide this type of information. Finally, you also will hear some direction indication. At 1 o'clock, here's the text, and that was meant to help the user to understand which direction the text was seen within the field of view. Here it goes.
It's a doorway. I feel like it's missing stuff. Maybe not.
At 1 o'clock, 231.
Okay, I missed stuff. Let's see. What are we getting used to?
At 1 o'clock, 231.
No, just more.
At 12 o'clock, 231. Tilt the device up. Rotate the device to the left. At 1 o'clock, 229. At 12 o'clock, 225 Maltau House, TNGN Word, Advisandel, Baskin Engineering New 226. AO Rose the Earliard, Undergraduate, ENU.
So I wanted to notice a few things. First of all, if you are walking without sight and using this system, keep in mind that you also need to avoid obstacles, maintaining your orientation, knowing where you are at all time. It's a real dual task here. You might have noticed that several of the name tags were skipped. He was not able to read them, and probably because he was moving so fast that the blur was such that not even our system were able to detect those. And then he noticed that in front of sign, he wanted to hear it multiple times because he couldn't be sure that the whole sign was read at once or not. It's a complicated interactive thing. Another thing we discovered through the experiment, which was a surprise to us, was that some of the people using this decided to actually explore the wall with their hand. And here is an example.
Faculty Services, September 19th, 27. Dynamics and control. Dynamics and control. 308. Dynamics and control log. And 308. Dynamics and control laboratory.
So this happened for the most time when they were testing with the Microsoft app. He quickly learned that there are name tags close to doors, so as soon as he would find a door, he would go and use their hands. We didn't thought of that, didn't think of it. Now, this is the only quantitative results I'm going to show. So here I'm showing the recall rate, which is the proportion of existing sign in an environment that was explored by these people that was actually correctly detected and read. All of the 7 participants tested both with the Microsoft app and with our own app. The results are showing in orange for our own app. And you say, oh, that's good. Apparently, this was not a competition against Microsoft, of course. They will win. But in a sense, we see that the fact that we can do some text spotting does help. In fact, some of these people were not able to find a single sign with a Microsoft app. However, for those who did hand exploration, they were the most successful, right? Because they really explored the world by hand. My students say they cheated. I said they didn't, because you do your task whichever way works. You know, if technology wins, good. If manual exploration wins, so much better. Although, of course, manual exploration is not always feasible for large signs that are far away, and not always you are in a situation in which you can touch things. The other things I really wanted to see is that the results are pretty poor. The best performing person did at best less than 80%. 1 out of 5 signs was not read. And for the other people, that was even worse. In spite of all this beautiful AI technology we have, accessing these things without sight is actually difficult. And the last thing I also want to say is that wouldn't it be great if instead of holding a phone in your hand, you could wear a camera? It's not very ergonomic to hold the phone in your hand, especially if the other hand uses a cane or a dog. This picture shows Paul Schrader, who works for Aira. Aira is a small company in San Diego. Disclaimer, I'm a consultant. They do a beautiful service. It's a subscription service. If you subscribe there, you're given these glasses that have a camera. And you can request a service from a trained agent who is remote, who accesses the video stream from your camera and can answer visual questions. So who is this person in front coming towards me? Should I go left or right, and etc. So this is really great. Now, if people were wearable cameras, I think our job would be much easier. Those of you who followed the fiasco of Google Glasses might be correctly pessimistic. I'm still somewhat optimistic in this. Now let me change subject here briefly. I want to talk about the way that people with low vision can access on-screen content on a computer. Now, if you have low acuity because of a central retinal defect, and you want to read some text, I forgot to say, this is in collaboration with my collaborator, Susanna Chang from Optometry in Berkeley. So if you want to read some text that is small, chances are that you will use a screen magnifier. You could buy some software, or you could use what is already in your own operating system. My Mac, I would do something like that. And I would have this screen magnifier that could read, okay, used by many persons with low vision. It can be difficult to operate with poor hand dexterity, like me, or when using both hands to type. So you see the whole screen is magnified, but only part of that is seen through the viewport of your physical screen. So you have to move it around constantly. You have to move the center of magnification. Another way to use that would be using what is called the picture-in-picture. So this uses the magnifying lens paradigm. It's another possibility of doing screen magnification. In both cases, you need to be actively moving this with your hands, which can be difficult for some people. So we thought, well, do we really need to use our hands? Can we do it in a smarter way? For example, if I know where you're looking at the screen, could I control the center of magnification automatically? So we decided to run an experimental study with 6 participants with low vision, recruited at Optometry in Berkeley. I designed the software that simply did screen magnification we attached a little eye gaze tracker. These are things they can buy for a few $100, connect to your computer. In fact, several laboratories, including mine, are working on algorithms to do eye gaze tracking from the camera in your laptop, so you don't have to pay a dime for that. So we had people read magnified text, both using a full screen and a partial screen magnifier, and we recorded where they were looking on the screen, the mouse track as they were moving, as well as picture from the face to train our artificial intelligence systems. And let me just show you, we got a lot of interesting data, but let me just show you one thing. This is a document that we asked them to read, of course, magnified. It's an intellectual document about pistachio cannoli cake by Martha Stewart. Can't go wrong with that. And so what you see, the colored tracks there, are the mouse tracks, the center of magnification as I move my mouse. Participant P4 was really good. It was really able to follow the text as he was reading that. Participant P3, not much so. It was very difficult for her to move correctly the mouse. This resulted in a very low reading speed. Same thing over a 3-column document. Participant P2 was very good at following the text. Participant P3 was a little bit of a disaster. It was extremely difficult for this person to control precisely the mouse, especially when everything is magnified and you don't have a lot of reference. Okay, so we want to use eye gaze to control, but how would that work? And I have a very silly animation here to show you how this would work. Here I'm showing what would be a screen that is magnified. You see a lighter region with some errors. The user will not see that. These are just for the system to know about those. The idea is simple. As you look at one part of the screen, for example, this is where your gaze is at. As you start moving to the right, as you arrive towards the end, to the edge of the screen, probably want to continue reading. And that's where the content should be moved to the left. So you're reading, you arrive at this portion here, and this is when the content should start moving to the left, so that you can go back with your gaze and continue reading. It's a very simple system. We implemented that, and we started some initial studies. These are extremely initial. And let me show you. So we have 2 screens here. These are the recording of the screens that people use them with magnification. For both screens, the red and the blue dots represent the location of your eye. Slightly different. That is just a technicality. The difference here is that in the left screen, this was moved by hand. With the mouse, you have to do what I just did before in front of you. The right-hand screen, the user was not doing anything, just reading the screen. And the system automatically knew where to move the center of magnification to enable this reading. This was actually the same user 6 months apart. So this was very exciting for us. It's just a proof of concept that it may be possible to use screen magnification with our hands and hopefully make it much easier to use for a lot of people. That concludes my talk. These are my sponsors and the awards that I received from NIH, NSF, Transportation Research Board, and Research to Prevent Blindness. I also want to thank the Vista Center for the Blind and the Visually Impaired of Santa Cruz, Palo Alto, and now Santa Clara. They give me a lot of advice, and they always participate as volunteers to my experiments, and that's really great. Thank you very much.